Okay, let's be honest. When you hear the word calculus, what comes to mind? For a lot of us, it's probably flashbacks to some pretty tough math classes. But what if I told you it's not just about formulas? What if it's actually a language designed to describe a world that is always, always in motion? That's what calculus is. Really, it's the mathematics of change.
To see what I mean, just picture something falling, like a cliff diver. They don't just drop at one steady speed, right? Gravity is pulling them faster and faster every single moment. Their speed is constantly changing, not just every second, but every millisecond, every tiny, infinitesimally small instant.
So, that leads to a really cool puzzle. Think about the speedometer in your car. It tells you your speed right now, in this exact instant. But have you ever stopped to think about how weird that is? An instant has zero duration. It doesn't last any time at all. So how can you be moving at all in an instant? This is a question where basic algebra just kind of hits a wall. It can't really handle it.
Okay, so how do we crack this nut? Well, we're going to come at it from a totally different angle. We're going to switch from the physics of a falling object to the geometry of a curve. It might seem different, but trust me, it's the exact same puzzle, just dressed up in different clothes.
And this is where it gets really cool. It turns out that finding that instantaneous speed is the exact same problem as finding the steepness or the slope of a graph at one single point. If we can figure out the slope at one tiny dot on a curve, we've solved the speed problem.
Okay, so how on earth do you measure the steepness of just one tiny point? The tricky part is, you can't. Not directly anyway, but we can be clever about it. We can sneak up on the answer by making a bunch of really good approximations that get better and better.
All right, check this out. We've got a curve here that represents our object's motion. We can't find the slope at one point, but what we can do easily is pick 2 points and draw a straight line between them. This is called a secant line, and its slope gives us the average speed between those 2 points. It's not the instant speed we want, but hey, it's a start.
So what happens if we start sliding that second point, Q, closer to the first one, P? Look at that. The secant line connecting them pivots and gets steeper. Our approximation of the slope at point P is getting much, much more accurate. We're zeroing in on it.
And here's the magic moment. Imagine we bring those 2 points so incredibly close that they're practically sitting on top of each other. Our secant line, it morphs into something new, a tangent line. It just kisses the curve at that one single point. And boom, the slope of that line is the exact instantaneous speed we've been hunting for this whole time.
So just to put a name on it, what we were doing with that secant line, that's called finding the average rate of change. It's really just that classic rise over run formula you might remember from algebra. It's a simple idea, but it's the absolute foundation for what comes next.
You know, this whole idea of inching closer and closer to an answer without quite touching it? That is a huge fundamental concept in calculus. It's called a limit. And the specific limit we just found by shrinking that distance between our points, well, it has a very important name. And that name is the derivative. The derivative is basically the finish line for our secant lines. It's the exact value they were all pointing to as the gap between our 2 points shrank down to nothing. It's the mathematical tool that turns our series of good guesses into one perfect, precise answer.
So, let's boil it all down. The derivative, that's the key. It solves the mystery of instantaneous change. It's the number on the speedometer for that falling object. It's the exact steepness of the curve at one spot. You could even think of it as a Rosetta Stone that lets us translate between the language of physics and the language of geometry.
Okay, but here's where it gets really mind-blowing. The derivative isn't just for physics problems or drawing lines on a graph. Nope, it's this universal concept that pops up, well, pretty much everywhere.
Seriously, think of the derivative like a master key. It unlocks the secrets of how things change, no matter what you're looking at. It lets us ask that one crucial question: how fast is this changing right now? And it works for a speeding car, a growing economy, or even the spread of a disease.
So in physics, the derivative is velocity. But in economics, it's telling you the marginal cost, like what's the cost of making just one more item. In chemistry, it's the speed of a reaction. In biology, it's the growth rate of a bacterial population. You can even use it in sociology to model how fast a rumor is spreading. It's wild. They all look like different problems, but underneath, they're all the same mathematical idea.
And don't just take my word for it. As the calculus textbook by Stewart puts it so perfectly, these are all special cases of a single mathematical concept,
the derivative. So you see, we're not just messing around with graphs and slopes. We're learning to use a tool that helps us understand the fundamental nature of how things change all around us. So, from now on, when you glance at your car's speedometer, or you see the stock market bouncing around, or you just feel a temperature drop, remember, you're literally watching the derivative in action. You're seeing the world through the lens of calculus. So my question for you is, now that you know what to look for, where are you going to see it next?